Hello Year 11. Much of this week's remote learning focuses on something you met briefly in Year 9 in right-angled trigonometry and Pythagoras' theorem. Your teachers will then cover with you exact trigonometric values, which I believe will be new to you, although not a massive revolution in your thinking. If you haven't done so already, please make sure you've read through the CGP revision guide pages that I've posted along with this assignment. There, hopefully, you will have met Pythagoras' theorem, which states that the sum of the squares of the two shorter sides in a triangle is equal to the square of the larger side in the triangle. A squared plus b squared equals c squared. Or, alternatively, the hypotenuse squared is equal to the other two sides summed together when squared. You should also have met the idea of sine, cosine, and tangent. That is the idea that if a given angle is the same, the ratio of any two sides will always be identical. So, for example, if x is 30 degrees, the ratio of the opposite to the adjacent will always be the same ratio, and we call that ratio tan. So that's all these things are, really, is a way of thinking about the known ratio relative to an angle, or vice versa. And we of course need to be able to use these to solve problems. Looking at a simple case first, you're given a triangle with two sides and you're asked to calculate the length of the third side. So as soon as I have two lengths and want a third, I'm going to be looking for Pythagoras' theorem. That is, I know that AC squared, my hypotenuse squared, is going to be equal to 4.2 squared plus 5.6 squared. Or alternatively, AC is going to be the square root of 4.2 squared plus 5.6 squared. I don't need to worry about my plus or minus here because AC is a length and so must be positive. And I can type that into my calculator, 4.2 squared plus 5.6 squared, all square rooted, to give me my value of AC as 7 centimetres, matching my units. Now, of course, we can be asked to apply this to more complex problems, such as here. ABCD is a trapezium. Calculate the length of BC. So we're trying to find this length here. So I look at this shape and I ask myself, well, how am I going to find BC? And the easiest way, it seems to me, is that I know length AD. So if I can work out what this length here is and subtract it from 12, I can work out BC. And I'll note that I've constructed a right-angled triangle here, give or take a few sloppy drawings on my part. And I also notice that I know the length of my hypotenuse and I also know the length of my base. This is a rectangle, so if AB is 15 centimetres, this is also 15 centimetres. Let's call this length x, just to be nice and clear. And so I can now use Pythagoras' theorem. I have two sides, I want a third, it's a right-angled triangle. And that's crucial here, it must be a right-angled triangle. So I know that x squared plus 15 squared is equal to 17 squared. Therefore, x squared is equal to 17 squared subtract 15 squared. I know this order of sides because 17 is my hypotenuse. The sum of the squares of the two shorter sides equals the square of my hypotenuse. So that means that x squared is equal to 17 squared subtract 15 squared, 64, and so x is equal to 8, square rooting both sides, centimetres. Once again, don't need to worry about my plus or minus because it's a length, so I know this is 8 centimetres. But I'm not done, I need the length of BC. Well, if I know this length here is 8 centimetres and the total length is 12 centimetres, BC must be equal to 4 centimetres. 12 subtract 8. We can also be asked to look at equations involving angles, so using your trigonometry. And generally, probably the most common way you've seen to refer to these is going to be SOHCAHTOA. SOHCAHTOA. That is, sine is opposite divided by hypotenuse, cosine is adjacent divided by hypotenuse, tan is opposite divided by adjacent. work out the value of x. Now I note here I've got an angle and a side, and I need another side, so I'm using trigonometry. I can't use Pythagoras here because I only know one of my sides. I label my sides relative to the angle that I care about. Here it's this 35 degrees. So firstly I label my hypotenuse, that's the longest side. So here it's x. Then I look to label my adjacent, that's the other side which is next to my angle. And then I label my opposite, which is the side that is not next to my angle and is also not the hypotenuse or the adjacent. Now once again, I need to know that this is a right angled triangle. SOHCAHTOA only works for right angled triangles. We will look next week at how to work with non-right angled triangles. So, I know an angle, I know my opposite, I want my hypotenuse. So I look for which one of these three has opposite and hypotenuse in. It's sine. So I know that sine of my angle, sine 35, is equal to my opposite, 20, divided by my hypotenuse, x. Multiplying both sides by x, dividing both sides by sine 35, I now can use my calculator. I just check my calculator is in degrees. I do that by seeing there's a little d in the very top line. Now for me that actually isn't the case at the moment, so I go into, not that one, I go into, sorry, shift and then mode, or setup actually as it is in this case, and then I look for number 3, deg, which stands for degrees, and now I'm in degrees. So I have x is equal to 20 divided by sine 35, so x is equal to 34.9 centimetres to 3 SF. And I just asked myself very quickly, is that a sensible number? Well, I expect it to be larger than 20 because it's my hypotenuse, and it's not ridiculously far away from that, so yes, that seems sensible to me. Another question you could be asked would ask you to find the angle, perhaps. So here, I want an angle, I've got two sides, again I know that's going to be SOHCAHTOA of some description. I need to label my sides. So here, x is the angle I care about, this is my adjacent, this is my hypotenuse. I don't know my opposite, so I need something with my adjacent and my hypotenuse, which is cosine. So cosine x is equal to my adjacent, 16, divided by my hypotenuse, 24. So cosine x is equal to 16 over 24. And to find x, I need to do my inverse function of both sides. Just like if I know x squared is equal to 4, I do the inverse of that. I square root to get x is equal to plus or minus 2. If I know cosine x is 16 over 24, I do the inverse of that to get x is equal to, remembering my inverse function is shown with a negative 1 in superscript. It's not a power, that's an entirely different thing, but cosine negative 1, so inverse cosine we would say that. Often you'll hear that said as arc cosine instead of 16 over 24. So I just need to type that into my calculator. I notice that on my cosine button above in yellow is cosine and then negative 1, so inverse cosine. So I press shift cosine and then 16 over 24, giving me my value, x is equal to 48.2 degrees, again to 3 SF. I asked myself, is that sensible? And yes, that seems about right to me. It's got to be between 0 and 90 degrees, and indeed, thinking about my 16 and 24, I do expect it to be about halfway between there. Now, of course, we can be asked to apply this to a more complex problem as well. Here is my example for this. Work out the size of angle BCD. First thing I'll do in an exam always is label what I need, give your answer to 1 decimal place. And you're given right angled triangles, that immediately should be screaming right angled trigonometry for you therefore, or Pythagoras, or maybe even both. And you're given this length here, 22. And as soon as I see that in the exam, I think, well, that's not all that useful to me, but it probably can become useful. Because indeed, if I want this angle, I'm going to need to know 2 of these 3 sides. And it looks like this is going to be easier to work out, because I know the whole length is 22, so DC, if I can find AD, will be easy to work out. So I go to this triangle, ABD, and I note that I want some length here. Let's call that length for now just x, because that means that this length here, DC, is going to be 22 subtract x. And so I've got an adjacent to my known angle, and I've also got an opposite to my known angle. SOHCAHTOA, that means I need tan. So I know tan 37 is equal to my opposite 9 divided by my adjacent x. Multiply by x, divide by tan 37. 9 over tan 37, should really be lowercase. And so x is equal to, I just type it into my calculator, 11.943, let's go. Notice I'm not going to one decimal place here yet, even though that's the final answer, because otherwise I'll have rounding errors through my answer. So I've gone to a nice, easy to work with number, but to much more precision than I need in the final result. Because then I know that this length here, 22 subtract x, I'm just going to type 22 minus answer into my calculator, is 10.057, again to 3 dp, centimetres. And then I want my angle, I've got my opposite, and I've also got my adjacent. SOHCAHTOA, again, going to be tan. Tan of the angle I care about, BCD, is equal to my opposite, 9, divided by my adjacent, 10.057. So BCD, again I need to do inverse tan of both sides, is equal to inverse tan, or arctan, of 9 over 10.057. And again, I can make use of the answer button on my calculator, shift tan to get inverse tan, and then 9 over answer, close brackets, giving me a value for BCD of 41.8 degrees, remembering they wanted it to 1 decimal place. And that's quite a complex series of calculations, but you're all more than capable of that. It's just about spotting what you can do. And if in doubt, I guess, you could just calculate a number of sides until you get somewhere with this, but it's very nice to be able to spot, well, they've given me that 22 for a reason, so let's see if I can split it up first. I hope that was useful. Remember that you can always contact me or your teacher for any help. Other than that, have a good week.